Good afternoon and good morning. Welcome to ICANX Youth Talks, Young Scientists Shaping the Future. Opens on every Tuesday, 8 p.m. Beijing time. My name is Peng Xi. I'm from Peking University. I'm the moderator today. So today, the topic of our presentation will be computational optical imaging and metrology. We are honored to have three speakers. Dr. Kyung, Professor Chao Zuo, and Dr. Maciej Trusiak. So our first speaker is Dr. Kyung An. Let me introduce her while she shares her screen. Dr. An Institute of Standard and a PhD degree in physics from the Korea Advanced Institute of Science and Technology in 2016. Her current research interests include super-resolution imaging, computational imaging, and methods for measuring the optical properties of virtual reality and augmented reality devices. She has received several awards, including the third place in the 2015 International Military Science and Technology Competition, the Kyung Most Outstanding Dissertation Award from KAIST, and the second place in SML Young Professor Award. So, Dr. An, the podium is now yours.
Okay, thank you. Can you see my screen?
Yes, we can see.
Okay. Oh, sorry. Okay. Hello, I'm Kyung from Greece. First of all, I'm extremely honored to be able to talk on ICANX. Today, I would like to present on the topic of the potential of reflective FPM as an industrial inspection tool. The table of contents is as follows. We will begin with a brief introduction to Fourier tychographic microscopy and reflective Fourier tychographic microscopy. Then we will discuss various research, including time reduction of misalignment correction and epi recovery using adaptive step size and whale optimization algorithm, and our recent research on UV FPM. Fourier tychographic microscopy called FPM, proposed by Professor Goan Jung of Connecticut University, is a computational imaging technique that enables phase calculation without the need for an interferometer. Let me provide a more detailed explanation through a figure. When obtaining a sample image using an on-axis beam, we obtain a circular signal limited by a cutoff frequency that is proportional to the numerical aperture NA of the objective lens in the Fourier domain. However, when illuminating the sample with beams having plus minus kx0 angle components, we can obtain a signal at the position parallel to the kx axis shifted by plus minus kx0 compared to the signal obtained through the on-axis beam in the Fourier domain. In other words, by stitching them, the cutoff frequency in the kx axis can be extended. Therefore, sequentially illuminating the sample with a 2D LED array and stitching the obtained images in the Fourier domain, we can extend the cutoff frequency as illustrated in the last figure. In this case, the system's numerical aperture NA becomes the summation of the objective's length NA and the illumination's NA. In FPM, the process of obtaining a high-resolution image using the method mentioned earlier is referred to as FP recovery. To explain this process in more detail, it can be outlined as follows. Step 1, initialize the complex amplitude of the high-resolution image as follows. Typically, the amplitude is obtained using images captured from the on-axis beam, while the phase is set to 0. Step 2, Fourier transform the high-resolution image and crop the data by the NA of the objective lens centered around the corresponding LED position. This becomes the Fourier spectrum for that particular LED. Step 3, inverse Fourier transform this spectrum to obtain the complex amplitude for the corresponding LED in the spatial domain. Step 4, after replacing the amplitude of this complex amplitude with the measured amplitude values obtained by illuminating the sample with the LED, perform a Fourier transform again. Step 5, crop this obtained spectrum centered around the corresponding LED position by the NA of the objective lens, and then add it to the previously obtained Fourier spectrum. Step 6, by repeating this process for all LEDs, the cutoff frequency can be extended in 2 dimensions. Considering this as one cycle, it is repeated until the phase of the high-resolution image converges. During this process, the spectra obtained from LEDs need to sufficiently overlap and be stitched together by using the LED's partial coherence to converge the phase accurately and quickly. As a result, as shown in the last figure, it becomes possible to obtain both the high-resolution image and the phase value of the sample simultaneously. I will more focus our discussion on reflective FPM. Unlike the transmissive FPM, reflective FPM offers the advantage of being able to measure industrial samples such as semiconductors, metals, and displays. This is why I have been interested in this topic. However, the research progress was slow due to challenges in alignment and issues with low signal-to-noise ratio. Reflective FPM, as shown in the illustration, employs 2 types of illumination. First is bright field illumination, which uses beams within the objective's numerical aperture to illuminate the sample. And second, dark field illumination, which uses beams that exceed the objective's NA to illuminate the sample. In the case of dark field illumination, LEDs located further away from the optical axis illuminate the sample with more oblique angles, and this accounts for the high spatial frequency components of the sample. However, the big oblique angle and distance from the optical axis result in low signal-to-noise ratio, ultimately leading to the challenge of obtaining high-resolution image. To overcome this challenge, we have proposed a new dark field illuminator using a parabolic mirror. Using this illumination, we could obtain a high SNR signal-to-noise ratio from the sample, regardless of how far the LEDs were positioned from the center. As a result, by using a 10x objective lens, we enhanced the system's numerical aperture up to 1.06, allowing us to achieve a resolution of approximately 250 nanometer. The image shows a photo used to verify the system's resolution using a USAF target. Next, I would like to mention the significance of misalignment correction. To obtain a high-resolution image using FPM, it involves 4 steps, including the previously mentioned FP recovery. First, the raw image captured by the camera, consisting of thousands by thousands of pixels, undergoes segmentation to make FP recovery more efficient. Second, there is a process to calculate and correct the misalignment of these sub-images. Next, the corrected sub-images go through FP recovery to reconstruct high-resolution sub-images. Finally, these sub-images are stitched together in the spatial domain to ultimately obtain a single high-resolution image. First, let me briefly explain the segmentation and stitching processes. There are a couple of reasons for segmentation. First, it aims to reduce the computational load that arises from repeatedly applying Fourier transforms and inverse Fourier transforms to images with thousands by thousands of pixels. Second, it fundamentally addresses the limited spatial coherence of the LEDs. For these reasons, we perform image segmentation based on considerations such as the LED spectral bandwidth, the size of the LED chip, and the distance from the LED to the sample. Additionally, segmentation helps prevent errors in image recovery, even when the LED's illumination is not perfectly collimated. Therefore, we typically divide the sample into n by n sub-images, recover each sub-image into a high-resolution image, and then stitch them together in the spatial domain to obtain the final image. Next is misalignment correction. No matter how well the LED array is aligned, there will always be some degree of difference between the theoretical positions and the actual positions of the LEDs. When such misalignment occurs with errors delta x and delta y in the x and y axis, and a rotation error theta about the z-axis, failing to correct these misalignments before image recovery results in a significant degradation in image resolution and quality as illustrated below. Therefore, it is very important to calculate and correct misalignment before the recovery process. Several studies have been conducted to address misalignment correction, and one of them is the misalignment error correction method developed at Shanghai Institute of Optics and Fine Mechanics in 2018, known as MCFPM. This method involves adjusting the misalignment errors, for example, delta x, delta y, and theta by varying their values within the range of minus 2 millimeter to 2 millimeter for delta x and delta y, and plus minus 1 degree for theta. These adjusted values are then substituted into the recovery equation to calculate the difference between the intensity of the ICE LED obtained from the calculation and the intensity of the image we actually measured for the ICE LED. This process is carried out for all LEDs, and the sum of these differences is used to compute an error metric, capital E1. The goal is to minimize this error metric E1 by finding the values of delta x, delta y, and theta that make the smallest error. By using this method, you can obtain high-resolution image with high quality, but it has the drawback of taking a very long time, since it requires applying MCFPM and calculating misalignment errors for each sub-image. Furthermore, reflective FPM splits the illumination into two parts, resulting in more than twice the lengthy processing time. To overcome this time-consuming problem, we focused on the segment-independent property of MCFPM. At first, we verified that MCFPM has a certain degree of tolerance to aberration through simulation. After that, we were able to minimize the time required for misalignment correction by using MCFPM to calculate misalignment error only once on the subimage with the finest pattern, and then applying this value to the entire set of subimages. As a result, we were able to reduce the time required to reconstruct a 1 millimeter by 1 millimeter image from several hours to approximately 980 seconds. By comparing the images with an integrated circuit captured using a 100x 0.8 NA objective lens, we confirmed that the image was well reconstructed, not only at the center, but also at the edges of the integrated circuit. However, 980 second is still considered quite a long time in practical applications in the industry. Therefore, we attempted to reduce the time required for the FP recovery process using parallel processing with a GPU. Since misalignment correction and FP recovery consume the most time in the entire FPM process, we focused on reducing time for those two processes. The goal of FP recovery is to find the object function and pupil function that minimize the difference between the measured intensity and the calculated intensity. If the step size to reach the optimal point becomes too sparse, it may lead to a shorter time to reach the optimal point, but it can also result in overshooting the optimal point. On the other hand, if the step size is set too small, it takes an extremely long time to reach the optimal point. To address this issue, we applied an algorithm called adaptive step size, which was proposed by Professor Chao Zuo, who is attending this talk. This allows us to optimize both the time to reach the optimal point and the stability. By using the adaptive step size for FP recovery and parallel processing of independent subimages with a GPU, we were able to reduce the processing time to less than 1/10 of the original time. Furthermore, unlike in the figure A, where subimages couldn't reach the optimal point and residual errors occurred due to the Y step size, using the adaptive step size algorithm as shown in the figure B allowed us to assemble images in the spatial domain without errors. Next, we used two-whale optimization algorithm to optimize misalignment correction. Misalignment correction involves optimizing an objective function with multiple variables. The whale optimization algorithm was designed for optimizing objective functions with multiple variables and was first proposed in 2016, inspired by the idea of whales moving in groups to capture prey. We used WA and compared the results to those of two state-of-the-art algorithms for obtaining misalignment error. A represents a high-resolution image of the full FOB, while B to E depict zoomed-in images of the regions containing the finest patterns from A. B is the on-axis image, and C, D, and E are the results of misalignment error correction using WOA, a genetic algorithm, and particle swarm optimization, respectively. The results show that at 100 iterations, particle swarm optimization exhibited a slightly faster convergence compared to WOA by approximately 0.4 seconds. However, as seen in the right image, WOA demonstrated significantly better performance in terms of image quality compared to the other two algorithms. Finally, let me introduce our recent research. We are conducting a study to improve resolution by shifting the LED wavelengths into the UV range. Last year, NIST in the US presented research using a reflective FPM using a deep UV wavelength of 193 nanometer to measure photomask patterns at the 80 nanometer level. In this research, NIST set up an experiment using 193 nanometer excimer laser and a high NA objective lens, both of which are bulky and highly expensive. Since the excimer laser has high spatial coherence, they use the rotating diffuser to prevent speckle noise caused by its spatial coherence. From last year, we've been experimenting in the UV range. We began by setting up a reflective FPM using 365 nanometer high power LEDs. The 365 nanometer LEDs give high intensity light, so we could cut the exposure time drastically and obtain data much faster than before. To validate the system's resolution, we used the USAF target and were able to resolve patterns in group 11, element 4, corresponding to approximately 173 nanometer. In the future, we plan to lower the wavelengths to the 193 nanometer level to develop a compact reflective FPM system with sub 100 nanometer resolution. Lastly, we explored the potential of using UV reflective FPM to measure the integrated circuit of smartphones to investigate whether UV reflective FPM can be employed as industrial inspection equipment. Figures B1 and C1 show the result measured with 100x 0.9 NA objective lens and 5-on-5 nanometer on-axis beam. Figures B2, C2 show the result measured with 10x FPM with 5-on-5 nanometer LED array, and figure B3, C3 present the result measured with 10x FPM with 365 nanometer LED array. As shown in the figures, we confirmed that the patterns in the circuit were more clearly visible when using the 365 nanometer LEDs. Additionally, patterns that were previously indistinguishable as continuous or discontinuous became clearly distinguishable. So in conclusion, there's still a work to be done to make reflective FPM a practical tool for industrial measurements. We need to improve the speed of measurement and reconstruction, expand the area we can measure, enhance reliability, and boost resolution, among other things. But there's a lot of research in this direction, and we are still starting to see some promising results. So we are confident that the day when reflective FPM can be used as an inspection tool is not far away. And this is the end of my talk. Thank you for your listening.
Wonderful, Dr. An. You've made a lot of achievements towards the application of the FPM into the visualization of the integrated circuits into industry, and also expanding, dramatically improving the numerical aperture and the resolution of FPM technology, as well as accelerating the reconstruction of speed of this wonderful technique. So I think we will have an very hot discussion during our roundtable round. So now let me introduce our second speaker, Professor Chao Zuo. So, I need to share my screen. I'm sorry. So Professor Chao Zuo is a professor in optical engineering in Nanjing University of Science and Technology in China. He leads the Smart Computational Imaging Laboratory at the School of Electronics and Optical Engineering in NJU UST. And he is now, although being very young, he is already a fellow of SPIE and a fellow of Optica, and listed as an Clariwhite highly cited researcher. And he has long been engaged in the development of novel computational optical imaging and measurement technologies with a focus on phase measurement imaging metrology. He has published over 200 peer-reviewed articles with over 13,000 citations. These researches have been featured on journal covered, including Light Science and Applications, Optica, LPR, Photonic X, Advanced Photonics, etc., over 30 times. He currently served as an associate editor of the newly launched journal termed Photonic X, Optics and Lasers in Engineering, and as well as IEEE Transactions on Computational Imaging. So let's welcome Professor Chao for his wonderful talk.
Okay, thank you, Professor Xu, for the kind introduction. So I will share my screen now. Okay, can you see my screen and the laser pointer?
We can see your screen, but not. Yes, I found the pointer.
Yeah,
Yeah, the
okay.
podium is yours.
So both my picture and my voice is okay.
Yep.
Okay. Thank you, Professor Xu, for the kind introduction. Hello, everyone. My name is Chao from Nanjing University of Science and Technology. It's my great honor to have this opportunity to join this wonderful event, IKX Youth Talk. I think in the previous talk, Professor Xi An has already give a nice overview of how to apply Fourier topography microscopy to reflective samples, for example, the industrial samples. So my talk is quite relevant. So I will also talk about computational phase imaging, especially for the phase retrieval, non-interferometric phase imaging, and intensity diffraction tomography. And I'd like to focus more on the biomedical imaging applications. So first, I'd like to briefly introduce label frame microscopy and optical microscopy. So we know that the optical microscope, invented for more than 400 years ago, has now become an indispensable and ubiquitous instrument today. So we use microscope in every day in many areas of science and technologies, for example, so for cancer research, biomedicine, cell biology, and medical diagnosis. So in particular, the fluorescence microscopy has achieved several leaps, from 2D wide field to 3D confocal multiphoton microscopy, and then to super resolution fluorescence microscopy. So greatly promoting the development of modern sciences. However, fluorescence microscopy suffers from several problems. For example, so we have the phototoxicity, photobleaching, and it cannot reveal the whole cell landscape. So it's particularly important to develop labor-free microscopy techniques. So we know that for the current wave, so the electromagnetic wave can be characterized by the phasor or the complex amplitude. So we have both amplitude and phase. We capture intense image, we get amplitude, the phase information is lost. So although most living cells and tissues are transparent, so they are actually phase object. So when light passes through them, so the phase is delayed in proportional to the refracting index and the thickness of the sample. So therefore, so the quantitative phase imaging, QPI, is emerging as a power tool for labor-free microscopy. So if we measure the phase, we can actually use phase to infer refracting index or thickness of the sample. So it can also be used to measure the 3D, the height or topology for some refracted samples, as discussed in Professor An's talk. So the most well-established approach for quantitative phase imaging is based on interferometry and holography. Actually, we learn from our textbook. So if we superimpose two beams, one current beam are passing through the sample, and the other beam is actually act as a reference beam. We superimpose these two beams together, we can convert the phase into the fringe pattern. So actually, the phase actually is encoding to the intensity called hologram or interference pattern. So in this, actually the off-axis holography setup. So we get this very dense fringe. If we take the Fourier transform, we select one order, plus one or minus one order. So then we do the Fourier transform. So actually we get the phase function directly demodulated from this hologram. So after phase unwrapping, remove the aberration, we get the quantitative phase of the sample. So this method is quite simple and elegant. It can be realized single-shot quantitative phase imaging for labor-free samples, biological samples like the live HeLa cell, like this. However, so this kind of interferometry quantitative phase imaging approaches suffers from several problems. For example, so it requires very complex optic configurations. It actually is very sensitive to environment variations, and it also has some laser speck noise issues. If the image optics is not perfect, we have some dirt on the lens, so we have such kind of laser speck noise. So how to actually overcome this issue is particularly important for their applications in optical microscopy, because imaging quality and image resolution is very important in these applications. So this issue, the above mentioned issue, can be addressed if the quantitative phase imaging can be realized without resorting to the interferometry. We call this non-interferometric phase imaging, or we call it phase retrieval. The phase retrieval, actually we capture intense image and we recover the phase from the intense measurement. So including the one just mentioned in Professor An's talk is tachography and Fourier tachography microscopy. And first, I'd like to introduce this one. It's called the transport intensity equation. Actually, it's a kind of a very elegant method to recover the phase from the beam propagation. It's based on the diffraction variation. So here is the TIE, transport of intensity equation. So it describes the flow of intensity along the optic axis and changes as the wave propagates. So you can see here, this term is the intensity derivative along Z axis is a beam propagation direction. So we cannot measure it directly, but if we take two images with slightly defocusing, so we can use this finite differential formula to approximate this derivative term. And here IXY is just intensity at the plane you are interested in. So in this case, the only unknown term here is a phase function phi. So you solve this equation, it's actually a second order ecliptic partial differential equation. You solve this equation, you get the phase function directly. So without any resulting to the interferometry, and it's fully deterministic. There's no need to do iteration. Advantages are obviously, so you can see there's no need to use laser, so the experimental system is simple and stable. So you only need to take several images at different propagation distance, so it's quite easy to build the experimental system, and there's no speck noise issue. However, so conventional phase retrieval approach like the TIE are still based on the current emission assumptions. So it uses amplitude and phase representations. So two fundamental theoretical questions to be answered for their applications in microscopy. So is what's the definition of the fifth meaning of phase for partial current field? And what is the quantitative relation between the intensity and phase for partial current imaging? Actually, it's very important because we need to use low current light source to actually realize quantitative phase imaging. So we need to answer these two issues. So to answer this question, so we derive a so-called generalized transport of intensity equation, GTIE, and gave a strict definition of phase for partial current field. It can be seen that phase, generalized phase, is defined as a scalar potential whose derivative is associated with the first conditional frequency moment of the Wigner distribution function. It actually is a calculation of the 4D partial current light field. So we also found that if the actually generalized phase of the source vanish, this means phase is flat, or the intensity distribution of the side light source is symmetric about the optic axis. In this case, the generalized phase reduces the well-defined simple phase when the illumination is symmetric about the optic axis. Actually, it provides us a foundation for quantitative phase imaging on the partial current illumination. Besides the definition of phase, another very important issue regarding to the current imaging is the resolution. It's a very nice paper written by Professor Gao and Professor Yuan. Is if we want to achieve better imaging resolution in a conventional current imaging system, we need to do synthetic aperture. Like we use off-axis emission, we can also use structured emission to do synthetic aperture. And the image resolution best we can achieve is twice NA of optical length. Actually is corresponding to the incurrent diffraction limit of a conventional microscope. But we seldom use incurrent illumination or current illumination in our normal microscope because we know that in a conventional microscope, we use partial current illumination or even incurrent illumination. So if we open up the condenser, the conventional current CTF becomes the incurrent OTF. So we get twice of NA of image resolution, 2 times better cutoff frequency of the microscope. So you can see if we open up the illumination, open up the condenser, we get better resolution. So actually, is a very classic results written in our even information optics textbook, and but this result does not even valid for imaging phase object because actually it's only valid for amplitude objects, for absorption object. For phase imaging, so we need to derive so-called phase optical transfer function on the partial current illumination. Actually, the image part of the complex OTF. So it can be observed that if we open up the condenser, you can see the phase contrast function vanish. This means we cannot see phase object on the bright field microscope with incurrent illumination. You have to solve this problem because if we open up the condenser, the illumination coherence is quite low. In this case, we can only see absorption. We cannot see phase. So how to solve this issue? So we need to do a illumination coherence engineering. So there we can't use this because it provides very little phase contrast. And we found that the matched annular illumination not provide a very smooth response for both low and high frequencies, but extends the image resolution into the incurrent diffraction limit. So this means we use such kind of partial current illumination. So it will provide both very high contrast for phase information, but also give you very high resolution up to incurrent diffraction limits. So in this case, we do the experiments. So based on a high NA annular illumination, so it's shown for the first time, so that the TIE phase imaging can achieve a later resolution up to incurrent diffraction limit, 200 nanometers. By using only 3 intense images with selective defocus. We capture 3 intense images, we do the deconvolution, we get the phase function, we get quantitative phase map up to the incurrent diffraction limit. So we also demonstrate this AR-TIE approach for long-term time-lapse imaging of HeLa cell deviation. So you can see, because this method is label-free, so you can see, so we can do long-term imaging of the live HeLa cell without worrying about phototoxicity and photobleaching. So you can see that we can count the cell number and calculate the confidence ratio of this cell. We also apply the AR-TIE to multimodal imaging of the HeLa cell apoptosis. You can see we can calculate the phase contrast DRC from the quantitative phase imaging without resulting any actual hardware. We can also split our field of view buffer to display phase control DRC images. Okay, let's return back to the phase transfer function. So we can see that, so for a perfect imaging system, so OTF is always real. So we can only see absorption contrast. There's no phase contrast. So we induce defocus. Actually, it's kind of aberration. So we can get some image component of the complex OTF. So we can do as we did in the transport intensity equation approach. But besides the defocusing, so we can also break the symmetry in the optical system. It's another way to produce phase contrast. As actually mentioned in Professor An's talk, we have the so-called Fourier topography microscopy approach. So I don't want to elaborate this technology because Professor An has already given you a very nice introduction to this technology. It addresses another very important issue of commercial microscope is a trade-off between the field of view and resolution. You can see we have a very large field of view. We use a low objective lens, but resolution is poor. We switch to high NA objective lens, we get better resolution, but field of view is compromised. So for conventional microscope, so for certain objective lens, we cannot achieve both large field of view and high resolution. So Fourier topography can overcome these drawbacks by replace the light source of the microscope by using a LED array. So if we turn on the LED elements one by one, it emits objects from different directions and captured by a low objective lens. We do the synthetic aperture in the Fourier space, and we recover the phase, and we also do the synthetic aperture in Fourier domain. You can see due to the support of the Fourier space become larger and larger, we get a higher resolution. And you can see the significant improvements of the resolution compared with the low resolution captured by using the on-axis illumination. Because we naturally use a low objective lens, we naturally have a very large field of view in this case. So we achieve both very large field of view and high resolution simultaneously. So the final resolution achieved by this Fourier topography approach is the sum of the NA of the objective lens and illumination NA, as mentioned in Professor An's talk. So we want to achieve a very high imaging resolution. We need to increase either NA OBG or NA illumination. So but increase the NA objective lens, we sacrifice the imaging field of view. So in this case, we demonstrate a resolution enhanced FPM by increase the NA of the illumination. So here we can see we use a dense LED array into an oral immersion condenser, and the illumination NA can significantly enhance, for example, from 0.5 to 1.2. So in this case, the final synthetic NA is up to 1.6. So in this case, we compare the results. If we're using a conventional LED matrix, it's free space FPM, you can see the resolution improvements. It's also very nice, but you can see we can resolve element 5 group 10 because the final synthetic NA is 0.4 plus 0.5 is 0.9. But if we use REIPM, we can further extend the frequency support significantly from 0.4 to 1.6, so that you can see almost all the elements in the target can be resolved. So consequently, because we use a 10x objective lens, so we have a very large field of view, and we can achieve 300 nanometer image resolution by using this low power objective lens. And you can see the final space bandwidth product is 15 times higher than that conventional 16x objective lens, but image resolution is comparable. And with this technology, we can observe 20,000 red blood cells simultaneously and resolve the subcellular details for each cell, like the neutral field. In the central field of view, we have both amplitude and phase information. So recently, we want to apply this technology to the digital pathology. So we improve our power of this REIPM illuminator and integrate into a conventional whole slide imaging system. You can see by using only a 15x 0.95 NA dry objective lens, we can achieve image resolution comparable to oral emergent 100x objective lens. So we apply this technology for right blood cell classifications without using any oral emergent lens. And we also develop a miniaturized FPM system with a cell developed short working distance objective lens. The NA is 0.35 and magnification is 6x. You can see the working distance is quite short. And by combining this self-developed object lens, and we also design a LED like illuminator like this, and we call this hybrid bright field and dark field synthetic aperture, because actually we, in the central position, we turn on all these LED elements and do the deconvolution. We get a bright field image up to 2 NA, and this is dark field ring. So we actually add up to the third NA. So we get final synthetic NA up to 1.05 with only 7 images in this case. So we can do highly efficient Fourier typography reconstruction. And you can see here is a whole field view is very large, 2.2 millimeter by 1.5 millimeter, and the final synthetic aperture is up to 1.05. And you can see the image resolution even better than the conventional 16x 0.65 NA optic lens. And you can see, but the FOV is much larger compared with this one. And for imaging phase object, we also need to derive so-called phase transfer function. You can see the phase transfer function actually is different from the amplitude transfer function, because you can see these two circles on the optic illumination, actually the sign is opposite. In this case, it will cancel each other at low frequency. This means the low frequency phase can only be transferred when the NA of the illumination match the NA of the object lens. So in this case, if we want to recover the low frequency of the phase information, we need to use matched annular illumination like this. So we derive so-called the high-speed FPM techniques based on annular illumination. So minimum, so we can only use 4 images to achieve twice of NA improvements. So we present high-speed imaging results of this HeLa cell mitosis at 25 Hz with a resolution of about 655 nanometer across this 10x object length. FOV is 1.7 square millimeter. So if we slightly increase the number of LED illumination from 4 to 6, so we can recover the pupil function, recover the aberration function simultaneously, with also resulting to adaptive optics hardware. So we demonstrate the long-term high-throughput live cell QPI, quantitative phase imaging with computational digital AO, adaptive optics, and we can secure the diffraction limit performance over an extended period of time like this. You can see it's about 15 hours. So we can get a sharp in-focus image during this long period. So far, I have only talked about quantitative phase imaging. So it should be mentioned that the quantitative phase imaging actually is not truth reading imaging modality. So it can only provide cell profile or topology. So in order to realize truth reading imaging like the confocal microscopy, so we need to recover the volumetric refracting index distribution. So we need to use so-called optical diffraction tomography. So the ODT, the principle of ODT is quite similar to the computed tomography. So the sample is different. For example, if we do the illumination or rotation around our body, so we get the computed tomography, X-ray computed tomography. So the image contrast is absorption. But if we do this similar procedure for CR, so we have this so-called optical diffraction tomography. So we recover the 3D refracting index of the sample. So the basic principle of the ODT actually is based on Fourier diffraction theorem. So if we illuminate the sample from different angles, actually we can recover a certain semi-sphere in the Fourier space. So if we actually illuminate sample from all possible directions based on the same setup, we get this donut-shaped 3D OTF. Also, in 2D, it's like the butterfly shape. So in this case, we recover a certain region in the Fourier space. So we get some tomography imaging capability. But conventionally, so how to achieve ODT, we combine the holography approach for phase imaging and combine with the ODT to recover the 3D sample information. So the sample, it relies on current illumination and complicated sample rotation or beam scanning device like the ground mirror or some DMD. To solve these issues, we also want to extend this ODT approach from interferometric to non-interferometric. So we have proposal called intensity diffraction tomography based on intensity only measurements. So our approach actually is also an extension of the conventional transportal intensity equation and Fourier typography microscopy. So this one is based on partial current illumination based on zero focus scanning And this one is even more obvious because actually the sample is naturally emitted by the sample from different directions. So this tube approach can be extended to different tomography without any modification of their hardware. So we call so-called transport intensity different tomography, TIDT, and Fourier ptychography different tomography, FPDT. So I will show you these results. So extend TIE to TIDT, we need to extend the 2D quantitative phase imaging to 3D. So we need to extend the 2D phase OTF to 3D OTF. So we derive so-called 3D phase OTF on the partially coherent emission. And we do a simple scanning along the z-axis, and we do a 3D deconvolution. Based on the phase OTF, we get the refractive index of the cell directly. So it actually it's an elegant extension of the 2D TIE to 3D ODT. Similar to the 2D case, so we also want to find the optimal aperture for 3D imaging. So we found that matched annular illumination is optimal for ODT in terms of both resolution and signal to noise ratio. So based on the annular emission, so we can also capture the intensity stack and do the 3D deconvolution. We get very nice 3D reconstruction of this pendula at incurrent diffraction limit resolution. It's like the confocal image, but actually it's a label-free image. And it can also implement based on sequential LED illumination. So actually in this case, you can see the 3D OTF is a two semisphere. So we keep and remove the other one. So we do the synthetic aperture without compromise the contrast in the 3D OTF. So in this case, we can also slightly improve the X resolution. So we achieve the 3D imaging resolution up to 300 nanometer laterally and about 15 nanometer X-ray. And the second one, we call the Fourier ptychography diffraction tomography, FPDT. You can see we also extend the 2D spectrum into the 3D spectrum of the scalar potential, and we replace our measurement in the 3D semisphere in the 3D space and do the iteration very similar, but actually we extend the 2D Fourier spectrum to 3D, and it can be observed that if we incorporate some very large NA measurement, you can see the support of the 3D spectrum can be significantly enhanced, especially for the along the exotome. You can see for the XY resolution, it improves a lot by using a 10x 0.4 NA object length. You can see the extra later resolution improves from 634 nanometer to 319 nanometer. Compared with the incurrent microscope, but you can see the X resolution significantly improves, even more significantly than the later resolution, like this, from around 6 micrometer to around 900 nanometer. So in this case, we can achieve very large view, and we do the CT for each unlabeled cell. You can see here is the high throughput optical diffraction tomography results with 4,000 HeLa cell in the whole field view. And we can see the laser resolution is about 388 nanometer, and the X resolution is about 900 nanometer. And the whole field view can accommodate 20,000 red blood cells simultaneously. And we reveal its potential for 3D imaging of a large population of unstained cell. So we can also enhance measurement speed. So actually, initially, it requires 3,000 cells, 3,000 image for 3D reconstruction, and we do this multiplexing, we can reduce the number of measurements significantly. And in this case, we can do it quasi real time in this case. Quasi, yeah, you can see here the whole field view reconstruction of the HeLa cell, and it's a magnified view, and we can do the tomography, we can recover the refractive index layer by layer, and we can further increase the speed of the measurements if only the matched annular ring is used. So in this case, we can enable dynamic 3D label-free imaging of the living C. elegans at 10 Hz in this case. And finally, I'd like to mention two very important issues of this. Our intensity diffraction tomography is a missing low frequency issue. Actually, is a similar problem appears in the FPDT approach, because if the object in focus, if the NA of the illumination does not match the NA of the object length, in this case, we can never recover the low frequency component of the sample. So in this case, we combine the transport intensity equation approach with the Fourier topography different tomography. So we capture additional diffuse image, and in this case, we do the iteration. We use additional diffuse image in the TR-FPDT reconstruction. In this case, we can combine the phase contrast with the angular diversity. So in this case, we can compensate the missing low frequency in the low frequency part of the Fourier space. You can compare the results. For conventional FPDT, so if the matched illumination condition does not satisfy, you can see the N of the objective length is larger than the of illumination. In this case, we can never recover the low frequency component of the sample. It's a bead, and you can see after our TR-IPDT approach, we can recover the reflecting depth of this bead very nicely. And also for this HeLa cell, you can see the low frequency component of the HeLa cell cannot be recovered if the matched illumination condition does not satisfy this case. Yeah. I think there's something wrong with the video. And finally is X-ray resolution issue. So you can see this is our support for our butterfly region of the OTF. You can see this XY resolution is much better than the Z along Z direction. So in this case, so you can see the elongation along the Z optical axis. So actually is quite normal phenomenon for the optical diffraction tomography. So, but actually we have another imaging modality. We call it actually OCT. So it's based on the reflection setup. So in this case, we can combine these two based on the advantages of the FPDT because it's only intensity only measurement. So in this case, we use wavelength scanning OCT to capture the back scattering light, and we use the FPD approach, illuminate sample from different directions. So you use the conventional FPDT to obtain this central butterfly region and combine the OCT approach to extend their spectrum support in the third dimension. Yeah, I need to maybe there's some problem with the yeah, okay, it works. You can see in the transmissive illumination mode, in this case, so it's conventional IPDT, and in reflective mode, so we illuminate sample by using different wavelengths. So in this case, you can see we first capture the transmitted light, and we fill in the central, the donut-shaped OTF, and after that, we switch to the incoherent back scattering light based on the wavelength scanning. So we fill in this missing cone region. So in this case, combine these two spectrum, we get a better resolution. We can resolve these two dots very nearby. You can see here is our result for two tailor-made fiberglass. They are actually stacked, but it cannot resolve by conventional IPDT, but incorporates the back scattering OCT, we can resolve these two fibers very nicely. And finally, I want to show you some instruments we developed based on the above-mentioned key theory and the technologies. For example, here by combining a programmable LED array and a tunable lens, so we can actually realize quantitative phase imaging and bright field, dark field, rainbow illumination, and differential phase contrast with a simple mouse click. And this system can also be made very miniaturized and put into our incubator. And you can see here is a multimodal imaging of our chick cell scratch from our mouse. You can see here is the quantitative phase, and we can also render the phase based on the digital phase contrast and the differential phase contrast, and we can also show the phase in pseudo 3D mode. You can see here is a cell synchronous cell profile of the chick cells. Finally, I'd like to conclude my talk, and in this talk, I talk about two methods for quantitative phase imaging resulting to the interferometry based on serial focus scanning is the transport of intensity equation TRE approach and Fourier topography microscopy on illumination scanning diversity. So this two approach can also be extended into the 3D tomography without any modification in their hardware. So we do the 3D intense scanning, we do a deconvolution, we get the 3D refraction index of the sphere. We also can use the extended Fourier typography from 2D to 3D. We can also recover the 3D scalar potential, 3D refraction index of the sync object. And to summarize, I think our research shows strict coherence and information and the longer prerequisites for quantitative phase imaging and optical diffraction tomography is very promising techniques towards a new generation of label-free 3D microscopy. Finally, I'd like to thank my students, colleagues, and collaborators, and especially Professor Lensless group at Nanyang Technological University and Professor Chen Chen's group in Nanjing University of Science and Technology. And a lot of works have been done by my students, especially Jiasong, Jiaji, and Zhou Shun, and Yao Fan. And thank you for your attention. I'd like to take any questions and comments after maybe finish all these 3 talks. Thank you.
Wow, thank you, Professor Zuo, for the wonderful talk. I have many questions to ask, but I would rather to leave all the questions during our roundtable session. So now let's welcome our third speaker, Dr. Maciej Trusiak from Warsaw University. So let me share my screen. Dr. Trusiak has already started his screen share, so let me do the introduction. Dr. Trusiak is an associate professor at the Institute of Micromechanics and Photonics in the Faculty of Mechatronics of Warsaw University of Technology. He received his BS, MS, and PhD in photonics engineering from the Warsaw University of Technology. And he then conducted postdoc research in the optoelectronic imaging processing headed by Professor Javier Garcia in the University of Valencia in Spain. In 2022, he received the habilitation degree and started his quantitative computational imaging labs, working in computational imaging, optical metrology, interferometry, quantitative phase microscopy, lensless coherent imaging, as well as fringe pattern analysis. This year, he received the ERC starting grant focusing at lensless label-free nanoscopy. He actively engaged in optical community, such as SPIE Award Committee member, chair of Interferometry Conference at SPIE Optics and Photonics Congress, associated editor at Optics and Lasers in Engineering, and acting as a reviewer for a variety of high impact journals. So let's please join me to welcome Dr. Trusiak for his wonderful talk.
Thank you so much, Professor Xi. I hope you can hear me and see my slides, right?
Yes, and before your talk, one more announcement to the audience. Since our audience has reached above 12,000 attendees now, I encourage all the attendees to type your questions in the Q&A session for all the 3 speakers, so that I will ask them for you, and you will gain answers from our roundtable session. Now the podium is yours.
Okay. Thank you so much, Professor Xi, for the kind introduction. And it's very my great honor and pleasure to be a part of this fantastic event, ICANX Talks. And I enjoyed a lot 2 talks by Professor An and Professor Zuo. Really, congrats, guys. You're doing amazing science. So next 30 minutes, I would like to show you some things that we are doing in our lab in Warsaw, in Poland, on lensless digital holographic microscopy. So we will switch to lensless mode, both into the coherent regime from incoherent and reflective. So lensless, transmissive, and coherent regime. So I'll be presenting the work of my group, which I'm very proud of, and I'm super happy that that I can be a messenger of all this good news that they work really hard to generate. And if you like what you see, then please do not hesitate to contact me, because we have many openings for postdoc and PhD positions. So feel free to contact me anytime if you like what you see next. And we are running a lot of collaborations. For example, great collaboration with Professor Chao Zuo's lab, and also with Professor Vicente Micó in Valencia, and Professor Balprit Aluvalia in optical nanoscopy group in Norway. But also we work closely with Polish biologists, neurobiologists, that they tend to drive our interest with their needs in bioimaging. And I'm really happy and honored to acknowledge all of these collaborations that make our group stronger and stronger over the years. Okay, so when we think about optical microscopy, often this device comes to our minds. But I have generally two problems with this fantastic device. It enables so many great applications. It's purely fantastic. But if you would like to image transparent objects like cells that are mainly made out of water, like we are made out of water mainly, the contrast is too low, which already covered by Chao Zuo perfectly. And if you would like to have high magnification, then the small field of view comes into play, as we have this trade-off between magnification and field of view. Let me tackle first very quickly the contrast, because Professor Chao Zuo made perfect presentation about it. I really enjoyed it. The idea is to switch domains from the absorption domain that we are encountering in classical microscopy to the phase, to refraction domain. So we are now sensing how the light is refracted by the sample and not how it is absorbed by the sample. And that's why we are gaining so-called phase contrast, because the light is refracted in different parts of the object by different means. And that's why this phase difference is different, and optical phase delay is different, and we can have very nice high contrast images like you can see here. So we need to record the data and reconstruct. So it's no longer what you see is what you get principle, but we are working in the computational microscopy regime. So record and reconstruct data. Afterwards, this was started nearly 20 years ago by Michael Feld's lab in MIT, and then by Christian de Persange in EPFL. So it's already well-established technique called quantitative phase microscopy. So I like to call it a fun bus drive. So we start from intensity town and we finish in phase guild. So when we think about coherent techniques, there is one step that we need to make, and it's called a fringe pattern station. And the fringe pattern is generated upon interference of two beams: the object beam that carries information about our object, and the reference beam. When they overlap, they create a quasi-periodic fringe pattern. So we are still in the intensity regime. We still do not have the phase contrast, but we can access the phase contrast by calculating actually how the fringes are bending in each position, because the bend, the local shape of the fringes, tells us the information about local phase delay, and phase delay associate information about refractive index structure and the physical thickness of the object, and voila, we have this nice contrast. And we need to use very low doses of lights, and so we can study non-invasively. Like here, we studied with Professor Balprit Aluvalia from Art University of Norway, fish cells in time-lapse regime for many hours, and then this is something that is can be done easily in a single shot scenario with very low light dosage. Okay, so it's very important to note that biomedical quantitative phase imaging is something that has 20-something years, but we are standing on the shoulder of giants of interferometry and digital holography that was already developed for many years, before starting from the 60s and 70s for the technical purposes. So it's a lot that we are actually using from interferometry and digital holography community, and we need to pay the tributes to that. Okay, mainly two things coming to mind, commercially speaking, when we think about quantitative phase imaging. It's the nanolife and tomocubes, but they are all bulky. So I would like to go lensless, and I would like to convince you that field of view matters. And why field of view matters? You can see it here. Field of view will tell us the context of our information. So when we know that something is bigger than our actually eye, that what our eye can see, we are pretty sure that we will miss some information, miss some context, and our inference will be flooded. And this is the example. Here, the dog is laying down. Here, the dog is standing. And here, this dog is sitting. But if we will be able to see the entire field of view, we would see that the situation is different. So each time we look closer into one particular spot with the entire field of view, we tend to make mistakes, and we need to make some inference, and this inference is fundamentally flawed. So that's why field of view matters. And another cartoon that supports this theory is this one. It's a well-known cartoon that only partial field of view imaging, which is limited by the microscope objective that we are using, will give us some limited information, and this should be the high probability that will be flawed. The inference would be wrong. So the field of view matters. That's why we are going lensless. So we are throwing out the objective, microscope objective, and we just use the sensor to capture the holographic shadow that object is casting while illuminated by the light source. So this is only the light source sample and the CCD camera in this scenario. The larger the camera is, the larger our field of view is. And in this situation, we have 13/9 millimeters of field of view with the live neural cell imaging, and we can track all the cells simultaneously, but we will get into that later on. It was started, the idea, by Kreuzer lab, and followed by Garcia Sucerquia work in Colombia, and of course with Professor Osgen lab in UCLA, and his postdoc Ewan McLeod, and many others. So it's not something new, but I would like to present our take on different problems that you may stumble upon in lensless microscopy. So first of the problems is that what you are capturing is an inline hologram. In the inline hologram looks like this. For example, for the human cheek cells, it's captured, and then the physical concept is really well established. It's like a Gabor holography. And then Gabor got a Nobel Prize for this in physics in '71. So we have this inline holography, very well for weakly scattering objects. And what we do is we repropagate. So we're always defocused because we cannot put the camera into the object. So we always work in some defocus that needs to be corrected numerically upon propagation. And if you propagate, because we use Fourier transform, we get for free the phase information. So now we have the phase and the amplitude, and some problems with that. Coherent artifacts, that mainly the twin image effect, which I will discuss. But firstly, I would like to discuss this autofocusing, because the idea is that we do not know a priori the distance for the propagation between camera plane and object plane. So we need to have this robust way to calculate it, and we propose the dark focus metric, which works very easily. So we have our input hologram. It is high pass filtered to remove the background and keep only the coherent term, only the scattering related terms of fringes that are scattering related. And this will generate, once propagated, a dark field, a computational dark field, which is similar to a physical dark field, because in physical dark field regime, what we are actually doing is we are forcing only the scattered light to form the image. And here we are not doing this physically, we are doing this numerically. So by high pass filtering, we are introducing this dark field regime, which already increases the sharpness, let's say, of the object, but then we calculate the gradient of the dark field, and then the variance of this gradient, it's a norm that will tell us the perfect location, precise location of the object plane. So this is a see-through stack from the amplitude regime. This is the see-through stack from the dark field regime, and this is the see-through from the dark field gradient. So you can see that we are capturing the sharpness by the variance of the gradients, and we are repropagating the hologram to many different planes, predefined planes, and we are calculating the metrics for every plane, and the maximum the metric shows us the object plane. We also have a nice paper when we accelerate it, and we can use only nicely predicted 5-6 planes, not entire thousands of planes. So it can be done quicker. Okay, so twin image phenomena is the main thing that limits us in lensless inline holography, because if you have an object, our camera does not know if the hologram comes from the left or from the right. because it would look precisely the same if our object would be transversed on the other side of the camera, because it's inline holography. All the information is mixed in the Fourier space. So both virtual and real objects are contributing to the field upon propagation. So if we are propagating this hologram from the camera plane back to the object plane, what we are actually receiving is this object in focus and this virtual object double out of focus. And we can see some fringes there. So on top of the sharply extracted information, phase and amplitude information, we have double the focused virtual twin image information. There are multiple ways to avoid this problem. I will briefly discuss iterative methods, deep neural networks, and off-axis reference beam microscopy. Okay, so by iterations, I mean Gerber-Saxton. We can go either multi-wavelength, so have multiple holograms with different wavelengths, or to go multi-height, so have different holograms with different position of camera. So change the magnification. There are some things. The single shot can be done using multi-wavelengths with color camera with multi-height. Not so good. Different magnification. The magnification is the same in the multi-wavelength approach, but in multi-height it needs a correction. Phase accuracy is high in multi-height, but in multi-wavelength can be so problematic because of the dispersion, because we use, after all, the different wavelengths. And how many holograms? Normally, typically 3 in multi-wavelength, and multi-height as many as needed. We use 8 to 9. What's wrong with this different magnification? When we move the camera, we change the geometry, the optical magnification of the setup. So everything moves and needs to be corrected. Of course, it can be corrected. We have this affine transform way developed by my PhD student, Mikołaj Rogalski, and it is working really nicely. But let us focus for now on wavelength multiplexing. So we do have 3 channels. So we have 3 holograms captured simultaneously at the camera: blue, green, and red holograms. So what he proposed, Mikołaj Rogalski, you can see his face here. He's a genius student of mine, PhD student, last year student. So he proposed to do something like this, to start with the blue. It's like a Gerber-Saxton approach. What he proposed is additional filtering. So we start with the blue hologram. We have phase and amplitude. Phase is missing, of course, because we didn't capture any phase. So we start with 0, and amplitude is corresponds to the intensity on the camera. And we go back to propagate to the object plane. And we have some approximation of the phase via Fourier transform, angular spectrum propagation. And then we use so-called complex field filtering that Mikołaj proposed to remove partially the excessive fringes coming from the double defocused virtual object, so the twin image. And then we go back with a different wavelength. And now in the camera plane, we have amplitude and phase, some estimation of phase. So we switch the amplitude by the registered amplitude, the green one, and we move forward with the iteration. So every time we stumble upon a place where we actually captured some data, we replace this data with the one that is converging to the complex field of interest. Okay, so this looks like this. We start with the blue one and finish with the blue one. One reason for that, to have the best resolution possible. And you can see here that with this Gerber-Saxton and complex field filtering, we can remove, increase the signal to background and signal to noise ratio by far. And we can also increase the resolution, because the resolution here is decreased mainly due to the numerical reconstruction errors, not to the physically linked things like temporal coherence or pixel size or geometry of the setup, because the setup is the same. We capture 2 or more holograms and we do better reconstruction. The reconstruction actually unveils more better resolution. We are not restricted to these problems with numerical reconstruction. And in computational imaging, numerical reconstruction plays a crucial role always. And here we tested on a USAF target and seen that the more holograms we have and the more elaborate our numerical processing is, the lower the noise, the lower the coherent noise, the lower the twin image noise, and we can preserve the object information. And we tested also this on the spermatozoa, and we can see that single wavelength angular spectrum is compared favorably. It's limited by the twin image errors, and then by moving to Gerber-Saxton and to this additional filtering, we are increasing the signal to background, the signal to noise ratio drastically. And here you can see the video, and the video you can see that the live spermatozoa are within this halos of twin image, and after our processing, it looks really nice, and you can even see the tail of the spermatozoa quite nicely. Okay, so we also studied neural cells because we work with neurobiologists. And if we have two holograms, then from the single hologram, you can see the face in the up row, and the down row, you can see the dark field imaging that we already briefly mentioned. And you can see that with double hologram, Gerber-Saxton, and with additional filtering, we are increasing the signal to background, the signal to noise ratio drastically. And this dark field is really, really nice. So let me spend one more slide on dark field imaging. So it's really easy to compute. So we have high pass filtering of the hologram, and that's it. And then we do the propagation, and in the amplitude of this complex wavefront, we have dark field imaging. And also what's nice that it's really, the signal is amplified. What do I mean by amplified? If we think about amplitude, pure phase, and mixed amplitude and phase objects, in a dark field, we still have some information. So the dark field is like a sum of amplitude and phase imaging. That's why, for example, for tracking, when we need a high signal to noise ratio, then it comes in handy because we actually join forces between the amplitude and phase signals, and we augment the final results. And so we used it to track cells, live cells. Here you can see only a small part of the gigantic field of view. And you can see that every cell is being tracked at the same time. So we have single cell precision, and the tracking resolution is way below the cellular size, so it's subcellular precision. So we are actually tracking the center of mass of each cell. We can see, calculate many parameters, for example, the speed, the average speed of the culture, the number of cells, and the confluence, and many more. And also what we can do is to limit the dimensionality of the problem, because we have enormous amounts of data with this gigantic field of views, hundreds of thousands of cells being tracked at the same time. So we can think about heat map analysis, like you can see after the football game. The heat map tells you the location, how frequently one player likes to reside in each side of the pitch. So when we do the same calculation for the culture of cells, we can see already some nice. It's a new domain of thinking about migration of cells. It's easy calculated. You just do the variance in each pixels over the time-lapse data. And when you overlay these two data, so the heat map and the cells, you can see very nicely where the cells like to be. And I think this is something that can be used to differentiate between different colonies of cell different migration behavior, but this is work in progress. Okay, so 2D tracking I already covered, and we also can do 3D tracking. And to do so, we came up with the engine to simulate the holograms with the given trajectories of objects, to be able to actually verify and benchmark and put the number on the accuracy of our tracking of our device in our trajectories. And here you can see that this beat is going in spiral, and we are tracking, and this is the errors are quite small. And also what we can do is this extended depth of focus imaging, because if for every instance, for every object, time instance of every object, we know with the plane of focus, we can depict all of the objects simultaneously at their focal planes. And then we will have the extended depth of focus. Maybe this one will be more compelling with more objects to see going often out and in focus. And yeah, you can, this is open access code. You can play with your trajectories as you want. Okay, and the quantitative numerical analysis shows that for many different concentrations and many different noise levels, generally X and Y error is way below the radius of the bit, and the Z error is way below the diameter of the bit. So we are perfectly happy about the tracking precision of our dark focus metric based on dark track imaging. We tested it on live spermatozoa tracking. You can see here some of the sperm cells, human sperm cells moving, and you can already discern the trajectories known as helical trajectories. And you can see here in this cube that the blue one will be enlarged, and we can see that the healthy helical trajectory can be spotted here. Okay, and we also tested it for the goat sperm, where much more is happening. So I don't want to be rude to the author of this material, but this is much more interesting. So many sperm cells moving in all kinds of directions. They will be still able to run the dark tracks smoothly on this data. Okay, so let's switch some gears from tracking to high throughput imaging, but of static things. For example, static is mouse brain tissue slice. And when we think about it, it's a perfect example for high throughput imaging because we need high field of view because it's a large brain, and we don't need to go scanning and stitching. With a small field of view, we just have the ability to image all at once. And this imaging is nice because our neuroscientists said that, for example, this red arrow points to something called cornus ammoni, and the blue points to something that's called dentate gyrus. And this is done without any labeling, and this is done simultaneously for entire field of view. So I think this is a promising way. You can see here in this in a larger magnification, and for this you can appreciate all of the features of the mouse brain. So the resolution is subcellular, and the field of view is gigantic to cover all the brain. And the brain is in bad condition. This slightly bad condition. That's why we got it from our neurologists, because they didn't used to use it anymore. But now we are running some trials on very nicely cut slices. Okay, so let's switch the gears to another way to limit the twin image. We can do this using neural networks. Also, it was done by my PhD student Mikołaj Rogalski. So he came up with this idea to use flower recognition database to create amplitude and phase targets, then to generate holograms, and then to propagate back to the object plane and have neural networks to be able to go from input images with twin image to the test targets without twin image, both in amplitude and phase. So actually not one, but two neural networks, one for amplitude filtering and second for phase filtering using this kind of architecture. Actually was heavily based on the work of Chao Zuo lab in Finnish pattern profilometry using deep neural networks. And you can play with the architecture as you wish with adding different pattern and filters. So the idea for physical consistency, so it's not end-to-end deep neural network because we are worried that it might hallucinate something or paint something, but the way to achieve physical consistency is actually really simple and clever with the idea of Mikołaj. So if you have this input hologram, then in yellow you can see the amplitude and phase with twin image. So we apply deep neural network to clear out the twin image of amplitude and phase, and then we propagate it back to the hologram plane and substitute that amplitude with the hologram recorded to force the physical consistency. That's why we gain a lot of information. For example, you can see it here. The ground truth has some fringe-like feature, which is completely not visible in angular spectrum. After filtering from neural network, it disappears and it comes back again after this additional physical consistency Gerber-Saxon single iteration. And this is a very nice touch, and it enables also in quantitative manners to lower down the errors. What's good about this network is that it's a generally universal one. So training dataset was on daisy, sunflower, and tulips, so flowers. The validation also on flowers, dandelion rose, but the test data set was completely not flowers because we were animals like dogs, elephants, butterfly, chickens. So that's why we know that this network has fair share of universal versatility. And also it looks very nicely in experimental evaluation and compares really nicely to multi-shot techniques. It's a single shot technique, especially when we think about face features that are here in these green arrows. And you can see that Gerber-Saxton, multiple Gerber-Saxton, and this CFF filtering that I described previously leaves the empty squares. So the low frequencies are not so well imaged, and this neural network actually fills in the boxes nicely. Experimental evaluation using cheek cells imaging also shows that what should be there is still there, while the twin image is removed. And also it works very fast as neural network. We need 8 hours to train it, but it works really super fast, so we can do live imaging on the neural cells. Okay, and it's open access. It's should be out in the OpticsExpress really soon. So off-axis reference really quick because I have, I think, 5 more minutes. This idea uses a second beam, so we are interfering experimentally, physically into the image, the hologram formation. So on top of inline Gabor hologram, we have off-axis illumination, and by off-axis illumination, we can perform the Fourier filtering that already was described by Professor Chao Zuo brilliantly. So I will just say that we use this Fourier filtering to have phase, and when we have amplitude from the inline holography and phase from the off-axis holography, both lensless, then we don't have the phase the missing phase problem because we fill in for the phase, and that's why the twin image is not is removed, and you can compare the removal of the twin image. However, we still need to use 2 holograms, one just inline and second off-axis. The question is, can we do it in a single shot? And the answer, fortunately, is yes. So the idea is to use the center of the mask to create the phase, and use everything outside the mask, so the negative of the mask, to capture the amplitude of the complex field. And by this means, we use the phase test target to actually compare these techniques. First, on the left is regular inline Lensless holography. Second is our method with the reference beam. And third one is algorithmic approach, already described by me with these multiple holograms. And we can see that overall, in a large field of view, and both in a large field of view and a small field of view, the twin image is removed very nicely with the resolution at the same level, Okay, one more thing I would like to highlight very briefly is that we can actually play around with coherent artifact minimization also in by experimental means. So what I'm talking about is using rotating diffuser. So to actually limit partial coherence, spatial coherence. So we are still, we are not affecting the temporal coherence, but we are talking about spatial coherence. So if we put here the collimator microscope objective, and we focus when we put diffuser in the focal spot of this microscope objective, and we rotate it, we do something that's called randomization of phase. And if this phase is where everything is well aligned, the phase is randomized, and it is all the speckles that are generated are actually being averaged out physically. It can come in handy when we have a lot of problems with different artifacts. I mean, fringe patterns coming from different, for example, this Fizeau effect that our plate has 2 front and back end, and this like the interference between multiple beam reflected back to multiple beam interference can be removed. Of course, the general the average intensity will be lower because of the averaging. It comes in handy when we have objects like this. So again, with this brain slice, coronal brain slice of mouse's brain. And here on the left, we can see the results before applying the diffuser, and on the right, after applying diffuser. And we can see that the speckle pattern visible on the left is removed, And that's why we will not longer have the ambiguity whether the speckles, whether they are darker or brighter, are actually part of a physical information about our slice or just an artifact. Okay, so to slowly conclude my talk, I would like to highlight that there are still a lot of challenges in large field of view lensless holographic microscopy. First of all, the resolution, lateral and axial, should be improved. Then the depth, imaging depth, in terms of highly scattering media, also requires improvement. Managing the data efficiently for bioapplication. I mean, this enormous data. For example, we have the camera that is 12 centimeters square of field of view, and the space bandwidth product is enormous because we have resolution about 2 microns. So it's gigantic, and the need to manage quickly the data, I think, should be in place. And also, we should increase the signal to noise and signal to background ratio, especially for the stick imaging conditions. So I would try to tackle all the problems in European Research Council grant called NanoLens, proposing the first lensless label for nanoscopy, hopefully in next 5 years. Would also be nice is to actually arrive to the point that we'll have optical sectioning in lensless microscopy, because by now what we are reducing is the virtual plane. So we have real planes that constitute our object, and we have tons of virtual planes. And by eliminating twin image that I described throughout this talk, we are eliminating the virtual planes, but still the real planes are there. For example, here we can see that they are still overlapping. So to be able to somehow decouple the information of refractive index and thickness signal would be nice. And it's already been highlighted by amazing talk by Professor Chao Zuo that we do need tomography for that. We are doing tomography in our lab. We are also doing the 3D two-photon nanoprinting, 2-photon polymerization. So, for example, here we printed the logo of our lab and our university, 8 microns apart, and we were able to do this optical sectioning and decoupling of refractive index from the optical thickness via tomography. What also can be done in tomography really nicely is that you can image cells with a very nice resolution and in 3D. For example, here there are neural cells, and each axon has the dendritic spines that are actually formed when we memorize something. So the ability to track the events of dendritic spines formation actually is really something that neurobiologists dream of, because it will give us evidence of quantitative evidence of memorizing something, learning something. And this is the human cheek cell again with the 3D mode. So yeah, the 3D life is done in 3D. So we do need an access to 3D to have better information about that we are doing. So it will also be really nice to push forward the lensless 3D imaging. And by that, I would like to acknowledge all the members of Quantitative Computational Imaging Lab. And I would like to highlight that we have open calls for PhD postdoc students. Please, if you like what you see, don't hesitate to contact me on my email put here. Yes, and this is the final image of a neural cell colony imaged by our lensless microscope. And I would like to thank you so much for your attention.
Wonderful talk. Okay, now I will invite all the speakers to open their camera so that we can move on to our roundtable session. Okay, now if you open your the ICANX website, you will see that we four are on the podium. So I will start with the questions from the audience. And actually, the first question is for both Anne and Chao. So the question is whether the label-free phase microscopy can break the diffraction limits and reach super resolution. So Anne, you go first.
Sorry?
So whether label-free microscopy, phase microscopy can break diffraction limits.
So you mean that FPM can break the diffraction limit.
As a matter of fact, I have noticed that you have used an 10x objective to achieve a numerical aperture of 1.06, right?
Yes.
So yeah, can you elaborate more on that regard?
Yes. Yes, true. FPM can break the diffraction limit by stitching the images from illuminating different angles and stitching the image in the Fourier domain.
Fourier, yes.
And by extending the cutoff frequency, it breaks the diffraction limit.
Yeah, I was wondering how can you, since it's kind of an synthetic aperture process.
Yes.
And you're using an air lens, so the refractive index itself is 1. So how through synthetic aperture you can yield a numerical aperture above 1?
I don't understand your question.
I mean, the synthetic aperture is like you have an virtual large numerical aperture objective. You just combine the Fourier domain to reach its limitation, but the theoretical upper limit for an air objective,
yes,
must be less than 1 in my regard. So is there anything else that I missed here?
When we used only on-axis image, your mention is right, because it is the NA is limited by the objective lens NA. But when we use oblique angle illumination, how can I say this one? Yes, when we use oblique angle illumination, we can how can I say it affects the it affects the cutoff frequency
angle, or
yes in Fourier domain it extend the cutoff frequency.
That I understand, but because NA equals to n times the sin alpha, and no matter how you increase the alpha, you always get the sin alpha is always less than 1. That's my point.
How can I express it? It's a kind of how can I say this one? Obtaining large area image by using moving stage in spatial domain. When we see in the Fourier domain, it's like how can I say this one? Increase the measurement area in spatial domain equals to cutoff frequency extension in Fourier domain. Am I right, Professor Zuo?
So maybe Chao actually did the similar how to say breaking the similar law of the diffraction precisely the diffraction limit. So Chao, do you have any comments?
Yeah, so I think the question from the audience is a really good question, because actually we know for fluorescence microscopy we can actually have several means to break the upper limits, especially for some we use some spatial diodes of fluorescence labeling materials. Actually, we can have to do the localization, single molecule localization. But for label-free technology, so as mentioned by Professor An, the best resolution we can achieve actually the sum of our illumination NA and the objective NA. So I'm not quite catch the question raised by the audience. Nominally, so we surpass the resolution limits of the object lens, but actually we don't surpass the resolution limits of optical microscope. is about 200 nanometers, so at the best. So if we want to enhance the resolution, so we should either increase the NA of the illumination or increase the NA of the objective length. So we prefer to increase the NA of the illumination to endorse the power of the illumination into the imaging optics, because actually the field of view is determined by the NA of the optical length. So we have low power length, we have naturally very large field of view, but the imaging resolution is poor. So we increase the illumination, we don't sacrifice the imaging field of view, but we enhance the resolution. As we did in typically in Fourier topography, we use high NA illumination and plus low NA objective length to guarantee very large field of view and increase illumination NA to get higher synthetic NA, which is the sum of the NA illumination and NA objective length. But as you mentioned, that because in the air, so the NA of the maximum NA allows for the both NA illumination and NA of objective length are both 1. This means the maximum achievable numerical aperture is actually similar to the increment diffraction limit of the optical microscope. So in my setup, so I use an oral immersion condenser to create very high angle illumination, but actually for the detection parts, it's only conventional 10x objective length. I think very similar setup for Professor An's setup. So we use low N collecting optics, but for to enhance resolution, so we should either increase the NA of the illumination or using I think short wavelengths, as mentioned in Professor An's talk. I think she used deep UV 200 nanometer wavelengths, so I think can show much better resolution compared with the visible range. But theoretically, I think for Fourier topography, it's somewhat disappointing, because actually we cannot achieve image resolution surpassing the arbitrary diffraction limit of a conventional optical microscope. But I think there are some other types of method can maybe it's possible to surpass this limit. For example, if we impose some actually constraint, for example, the support constraint, if we assume the object is sparse, maybe we can increase some knowledge to do this, to surpass this 2NA limit of the conventional label-free microscopy. And for example, we can combine some, for example, microsphere imaging. So we have some other means to enhance resolution for label-free microscopy, but for our conventional phase imaging, actually it should be belong to the linear imaging optics. So it cannot surpass the NA limit of the resolution limit. I'm not sure, so I think Maciej maybe can have more opinion in this question.
Yeah,
I agree completely with you. So there is something that need to be said. So there is upper limit, which is physical limit, and we are not surpassing this limit with label microscopy. What we are surpassing is the capabilities of a given microscope objective, and that's it. So the upper limit is still there, and maybe if we think about localization, as Chao said, maybe if we could find a way to label-free make something blink, something sparse blink, and then we can actually every blinking is like is like a spherical wave. So if we then in time, so we need to, there is no free lunch, so we need to have something worse. So example, if we said that our time resolution will be worse, and we're capturing all of these spherical waves coming from different blinking label-free things, then we can do something like is being done in fluorescence, like single molecular localization. But right now I don't know any works on that. So right now label-free phase imaging is still upper limited.
I see. Yeah, thank you all. I think with your all of your explanations, I think the audience gets the accurate answer to the wonderful question. So the next question is for Professor Chao Zuo. The audience asks, I would like to know if real-time 3D imaging is currently achievable for label-free microscopy, especially in the case of high resolution and large sample volumes.
Yeah, it's also a very nice question, because actually what the result I show in my talk is actually based on post-processing. So only for quantitative phase imaging is kind of 2D, 2 and 5D we have mentioned. It can be done in real time. But for large field of view, high throughput imaging, so we normally need to capture quite a lot of raw data, and we do the synthetic aperture even in 3D. So actually, the final image data is quite large. So initially, for example, in Fourier topography, different tomography, we need to collect many hundreds of images. Initially, we use I think 3,000 images initially, but we reduced to tens of images per volume reconstruction. But it also need to do a lot of digital computing, because actually the whole field of view is very large, also very similar in Maciej's lens-free microscopy, because actually we need to cut the whole field of view into small parts and do actually it can be accelerated by GPU processing. But to do everything to reconstruct a very large field of view, large volume in real time is quite a challenge. So we are also try our best to optimize our algorithm and digital processing, especially to implement everything in C++ in GPU parallelly. So hopefully it can actually achieve real time and high throughput imaging, and either for a topography microscopy or not for the lens-free microscopy. But it's possible, but currently it's quite challenging.
Yeah, and a subsequent question following this one is I noticed that in your presentation you have an ultra large objective to do the high high resolution and high large field of view simultaneously. So how fast is the current status of this technology?
So it depends on how many illumination we use. Actually, for our current illumination, the power is sufficient and the speed, the data acquisition speed is limited by our camera. So actually, so it's very fast. But the processing is also depends on the data you use. For example, for Fourier topography, so if you want to enhance resolution, you need to capture a lot of dark field image. So it will increase the data amount. In that case, you will incorporate all the measurements into the Fourier space. It takes quite a lot of time. But for for example, high-speed imaging, especially for live here, so we can use 4 or even 6 images per reconstruction. In this case, it can achieve real-time, of course, real-time reconstruction. But for the whole field of view, large, very high throughput is quite challenging, especially for both 2D large field imaging and 3D different tomography. So we need a lot of data. So in this case, it's quite difficult to real-time processing.
Sure, fully understand. So the other question from Dr. Joan Wu, I think is for Maciej. So the question is, why can UTIR net achieve low frequency filling while removing twin images?
Why it can achieve that?
A kind of network like it's termed UTIR net.
Yeah, this network. Yeah. So this is a very good question. So it's not generally for all low frequencies. It has problems with low frequencies as many phase imaging techniques, but it can do better than Gerber-Saxton algorithm, because Gerber-Saxton, when we think about this box, then in the middle of the box you have this dark twin image effect. So it is not. There is no such thing as removing twin image effect. You can only minimize that to some extent. And this extent that we can minimize that we're using network is better because it works on a different. It uses only one iteration, but it works on a different assumption. The assumption is that we will through learning process have a network to remove the twin image for generally, not for a given object. And this the low frequency part, as I said, not all low frequencies will be recovered, but it is better than the Gerber-Saxton algorithm. It of course will depend on how the twin image will look like in the object. So it will depend on the focus distance that will capture the data. So that's why this network is prepared for a given geometry of the setup. So if you have a sample and the camera, and for a given distance, it will work nicely. But if you change the distance, not so much, it will work with small errors. But if we do change the distance significantly, then the entire phenomena of twin image will change, and you will need to redo the training of the network. So probably this answers the question. So it's not the super universal solution. It is thought for a given geometry with some buffer, but generally speaking, yeah, it works. It categorizes the error better than the GS algorithm, because
Okay,
GS
excellent.
learning.
I see. Okay, the next question is for Chao again. So when you don't match the illumination, you use TIE can compensate for the low frequency. Here, when you don't match the numerical aperture of illumination, does it has any range limit?
Yeah, it's also it's a good question, especially for theoretic part. So in our method, you can see, so we have two types of phase retrieval method, which TIE is based on defocusing, and the Fourier typography is based on off-axis illumination to break the symmetry of the object axis. But actually, for Fourier typography and the Fourier diffraction, for typography diffraction tomography, so we actually usually put a sample in the nominal in focus plane. So in this case, if we want to reconstruct the low frequency components, so the illumination angle should be match the NA of the object length. In this case, we have the two pupil in the Fourier space, they don't cancel each other, so we can recover low frequency component of the object. So in our experimental system, so we normally we use very large NA. I think as large as possible, so to increase the support range, the support coverage for our final synthetic NA. But usually we, for example, for oil emerging optics, for example, we use 1.6 NA or emerging object length. In this case, quite difficult to match the illumination to the NA of the object length, because usually the illumination is not illuminated from the same object length for the transmissive setup. So in this case, for example, we use 0.6 NA for the conventional condenser to match oral emerging optics in this case. So we have some certain missing frequency regions in the low frequency component of the spectrum. So in this case, we need to do additional defocus to produce additional phase contrast for the low frequency components. But as asked, I'm not quite catch the problem. Is there any range for the illumination angle? So theoretically, it should works for any case. So the extreme case is actually the on-axis illumination. In this case, it becomes a TIE approach because no synthetic aperture, again, from the off-axis illumination. But we use defocus to recover the phase. But I think a better choice should be we use as large as possible illumination angle. So at that case, so if we don't match the NA of the object length, then we use additional defocus to compensate the missing low frequency region. So in this case, I think this two method, the advantages of the two methods can be combined together. Hopefully, I answered the question.
I think so. I think you have covered the question very well. So the last question is for Maciej. So how fast can current lensless holography reach, and what is the lower limit of the frames that is required for a successful reconstruction?
That's a great question. Right
now,
yes.
One more question from me, which is what is the current limiting factor for the resolution or the speed?
Okay, so the limiting factor, I will maybe start with the limiting factor. I think is the size of the pixel. When we think about upper limit, we have small, generally, when we have microscope objectives, the NA is written on the objective. In the lensless imaging, the effective NA comes as a dance of many parameters like temporal coherence, spatial coherence, pixel size, sensor size, wavelength, numerical reconstruction, and so on and so on. So currently, in my opinion, what is limiting us is the pixel size. We can do pixel super resolution. We are trying to do this right now, but it would be nice to have pixel, let's say, wavelength scale pixel. That would help. That would help a lot. And in 3D lensless imaging, I mean this what limits is the low NA, the effective NA, and with the lack for now the ability to fill in the 3D Fourier space as densely as with the objectives. So as for speed, right now we are tackling this problem because it comes into play when we think about bio applications. So of course it depends on the size of the image, but in principle, if we have a single hologram to be reconstructed, that means that we need to propagate. A propagation is a Fourier transform and then an inverse Fourier transform, and there's something in between that we play within the Fourier transform. So the Fourier transform is really nicely optimized. So I cannot give you a one number, but the more holograms we need, for example, to improve the signal to background ratio, the lower will be our speed. But if we think about capturing data and then offline processing, then what limits us is the camera throughput. If we think about single shot, for multi-shot, for example, 3-shot techniques with wavelength multiplexing, still it is the limitation because we can use RGB cameras. So I would say that offline processing is limited by the camera shutter, by the camera speed. But if we would like to do this processing on the fly, that would be much lower. It would depend strongly on the ability to transfer data, process it, and visualize it. And but it comes down to a Fourier transform, and it scales, the complexity scales with the size of so for cameras of 12 centimeters square would be much bigger than for the smaller cameras. But I think 500 over 500 pixels, it would be easily more than 8 frames per second with all the processing to have this online visualization at some point. And then the tracking again is additional computation. So that's why I mentioned that the data management should be in place, because we have enormous data, like Professor Chao Zuo said, with the Fourier technographic microscope. Similarly, a lot of data. And here with the time lapses, for example, we're capturing data for 5 days every 5 seconds for this entire field of view, and then we need to do the tracking and say something about the cells. So this is a lot to process.
Yeah, physical constraints for the cellular tracking. So another question related to tracking is I would like to ask about the work on tracking. How is it possible to realize the determination of the z-axis in the direction? Is it possible to do the tracking through training and at the same time get the autofocus distance?
Yeah, that's a good question. But what we are doing right now is we are having this projection. So from 3D we go to 2D. Then we are generating the information about the object. So we are segmenting the objects, and then within each segmented object we apply dark focus to find the z distance. So in principle, yeah, the tracking is done by many other groups via deep learning, but I cannot say anything about the accuracy. It would be nice to do this trial, for example, use our software to generate the trajectories and then play around with different methods to see the accuracy. It never been done. There was some like segmentation and cell tracking. It was done in 2D. I think it was like a cell tracking event or something like that. But for the 3D tracking, I don't think that it's a benchmark. It's benchmark. So maybe it's a nice idea to join forces and try to do some kind of benchmarking of 3D tracking.
That's wonderful. Okay, time is up for our round table discussion. And please join me to thank all the three wonderful speakers. Now, let's move on to the awards to the three wonderful speakers. So the first speaker, Hee-Kwon An from Korea Research Institute of Standards and Science. And we gave a certificate for her seminal work on the potential of reflective of FPM as an industrial inspection tool. Yeah, congratulations. So you may notice that Anne has a lovely Chinese name, An Xiqing, and on the first page of her slide. Yeah. So from internal communication, we noticed that she can speak quite fluent Chinese as well. So 喜庆 恭喜你 congratulations. Yeah. So now please join me to give the certificate for Professor Chao Zuo for his wonderful work on the computational phase imaging for label-free 3D microscopy, especially non-interferometric phase retrieval and intensity diffraction tomography. Chao, congratulations.
Okay, thank you, Professor Xi. Thank you for all the audience. It's my great honor to present in this event. Thank you so much.
Sure. And the third award is given to Dr. Maciej Trusiak from Warsaw University of Technology for his seminal work on lensless digital holographic microscopy for high-throughput computational bioimaging. Yeah, congratulations, Dr. Trusiak.
Thank you so much, Professor Xi. Thank you so much, Chao Zuo. Thank you so much, Professor An. And thank you all the guys that watched us. And I'm really honored and deeply pleased to be here with you. And thanks so much again for your kind invitation and having me.
Thank you. I enjoy all of your talks very much. Now, the advertisement of our next week YOS talks. We will discuss about multi-field coupling and applications with 5 panelists and 1 moderator. So you're welcome to join us again on next Tuesday. That concludes our YOS talks today. Thank you all for joining us. Thank you, and have a good evening.
Thank you.
Bye-bye. Bye-bye.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。 我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡。